Welcome to part 3, and this time we'll be looking at how to work out the magnitude of the voltage source and the resistance in a Thevenin equivalent network. For now, we will assume that a Thevenin equivalent network exists. So let's consider what the voltage between the two terminals would be if there was nothing connected between the two terminals at all. This is known as the open circuit voltage, which I've written here as VOC. Now, with nothing connected between the two terminals, there will be no current flowing around this circuit, which means there'll be no voltage drop across the resistance RTH. And if there's no voltage drop across the resistance RTH, then the voltage here would be just equal to the voltage at A, which means the voltage that we're measuring between B and A would be the voltage across the voltage source VTH. That's the voltage in our Thevenin equivalent network. So the Thevenin equivalent voltage, VTH, is just equal to the open circuit voltage. And since the Thevenin network behaves exactly the same as our real network, the open circuit voltage of our real network would be equal to the Thevenin equivalent voltage. That just leaves the problem of how to work out the Thevenin equivalent resistance. This you can do by connecting a wire between the two terminals of the network. This is known as a short circuit. And then measuring the current flowing between A and B. Well, if you look at the Thevenin equivalent model, the current flowing through A and back through B would just be VTH divided by RTH. And that is known as the short circuit current. And we could measure this for our real network as well, the current flowing between the two terminals when they are connected directly together. Since we already know VTH, and we know that the short circuit current is VTH divided by RTH, we can work out RTH. RTH, the Thevenin equivalent resistance, would just be equal to the Thevenin equivalent voltage divided by the short circuit current. And the Thevenin equivalent voltage is the open circuit voltage, the voltage that's measured between A and B when there's nothing connected. So we can determine our Thevenin equivalent resistance by just taking the ratio of the open circuit voltage of our network to the short circuit current of our network. We can see that working. Let's go back to the example we were looking at earlier, but this time imagine that I don't know what the voltage and the resistance should be set to in the equivalent network. I can determine the open circuit voltage by just connecting nothing to the network of interest and just measuring the voltage across its two terminals. Reminder, an ideal ammeter has no resistance. An ideal voltmeter has an infinite resistance, so it behaves like an open circuit. There is no current flowing through an ideal voltmeter. So this 3.75 volts, that would be the open circuit voltage. And I know that should be the voltage in my equivalent network. Now, I need the short circuit current if I'm going to work out what the resistance in the equivalent model should be set to. So let's just put a short circuit across the outputs of our network, and I'll see the short circuit current is 5 milliamps. So the resistance in my Thevenin equivalent model should be the open circuit voltage, 3.75 volts, divided by the short circuit current, which I can see is 5 milliamps. And 3.75 volts divided by 5 milliamps is 750. So that is the resistance in my Thevenin equivalent model. And now these two circuits should work the same. For any load that I attach to their terminals, including a nonlinear load like a light-emitting diode. I can do a simpler example, although this time using a bit of algebra. Here I've got a potential divider, and the two terminals of my two-terminal network are across the output of my potential divider. So I know immediately that the voltage source here, which will be the voltage between A and B when there's nothing connected to them, the open circuit voltage, is just the output voltage of this potential divider. So my Thevenin equivalent voltage would just be V times R2 over R1 plus R2. The short circuit current would be the current that flows when A and B are directly connected together. And if I directly connect them together, then I would have effectively this circuit. Well, all of the current through this resistor would flow down through the short circuit. None of it would flow through the resistor. With just a wire connected across the resistor, the voltage here will be the same as the voltage here, which means that all of the voltage from the voltage source here will appear across this resistor. So the current flowing through this resistor, which is the current that would flow through the short circuit, is just V divided by R1. That's my short circuit current. So my Thevenin equivalent resistance, which is the open circuit voltage, divided by the short circuit current, would be, the V's cancel, this would be R1 R2 over R1 plus R2. Now, you might recognize that formula. That is the formula for the total resistance of two resistors in parallel. Is that a coincidence? No, it's not. And it gives a hint to a shortcut that we can often use to work out the Thevenin resistance of these networks. The shortcut goes like this. Supposing we have a two-terminal network which consists of independent voltage and current sources and some resistors. And I should warn you at this point that this trick only works if the voltage and current sources in our network are independent, in the sense that they're not functions of the voltage or current at anywhere else in the network. Now, this is a linear network, so the output voltage there, the open circuit output voltage, will be some function of all of the voltages and the currents in this network. I would have to be able to write something like this, where the Xi's are the sources, the independent current and voltage sources, the C's are constants. Equally, if I connected a wire between these two terminals, I would have the short circuit current flowing through that wire, and the short circuit current would also be a linear function of the independent sources in this circuit. The ratio of the open circuit voltage to the short circuit current is, as we know, the resistance in the Thevenin equivalent circuit. Now, what happens if I increase all of the sources in the circuit by a factor alpha? Just multiply them all by alpha. The open circuit voltage would increase by a factor of alpha. The short circuit current would increase by a factor of alpha. If all of the independent sources, all these X, get, for example, doubled, then VOC would double. If they all treble, VOC would treble, and so would the short circuit current, ISC. In general, with a factor of alpha increasing them, we would end up with this. Alpha times the original open circuit voltage and alpha times the original short circuit current. The two alphas would cancel out. The Thevenin resistance would not change. We can multiply all of these sources by the same factor alpha, and the Thevenin resistance does not change. Right, what happens then if alpha equals 0? RTH wouldn't change. So we could set all of these voltage sources and all of these current sources to 0, create a much simpler network, look at the resistance between that point and this point here, and that would be our Thevenin equivalent resistance. In the case of this network here, I would end up with something like this. I've just set all of the sources to 0. The current sources end up as just open circuits, nothing. There was one there, there was one here, there was one down there. But when they're set to 0, no current can flow through them. The voltage sources I've set to 0 and replaced with wires. Now, if I look at this circuit and ask, what is the equivalent network to this network? Well, this is just a network of resistors. It's going to have an equivalent network, which is just a resistor. The current is going to flow down through this resistor, and back to this terminal here. These two resistors aren't going to take any part in this circuit at all. They don't go anywhere. So if these resistors were A, B, C, and D, then the resistance in my Thevenin equivalent circuit would just be C plus D. This is usually considerably easier to work out, but as a reminder, this only works when the sources are independent. At this point, some mathematicians might say, hang on, if you set alpha equal to 0, then you're doing a division by 0 here. You can't divide by 0. At which point the engineers would say, okay, let's not let alpha actually go to 0, let's let it be 0.000001 times 10 to the power of minus a billion. At which point we can say that all of the voltage sources and the current sources are negligible, and to all practical purposes we can assume they're 0 and just carry on happily. Here's another example of applying this technique. If I set the independent sources in this circuit to 0, the current sources would just disappear from the circuit because they just behave like open circuits, nothing. The voltage source would appear to be a wire. A 0-volt voltage source just behaves like a wire. And this circuit would become this circuit. And the resistance between A and B there is just R1 in series with the parallel combination of R2 and R3. So in this case, I would end up with a Thevenin resistance of R1 plus R2, R3 over R2 plus R3. And this is often easier to work out than the open circuit voltage, the short circuit current, and then dividing them. Okay, that's all for this time. Next time, we'll have a look at a couple more examples.